Today we will study this graph realization problem. What this problem means and what is this Havel Hakimi theorem. So this is our topic for today. So let's start. First, let's see what is this problem. Let's discuss this problem statement. What is this graph realization problem? Graph realization means, can you realize a graph? If I give you some conditions, then can you realize a graph? Some condition I give you, like for example, I give you this degree sequence. This degree sequence I give you, like maybe 4, 3, 2, 2. This degree sequence I give you, and then I ask you from this degree sequence. So remember, this is a condition that is given to you, that this degree sequence is given to you for some graph. This is a degree sequence for some graph. I don't know what graph, but for some graph, this is the degree sequence for some graph. Okay, I don't know which graph. Now you have to tell me, with this degree sequence, only with this information, no other information you have, only with this information, can you realize a complete graph? Can you realize a complete graph? Can you realize a complete graph? The answer is no. The answer is no, because in a complete graph, your degree sequence should be same. If you have km, then your degree sequence should be m minus 1, and so on, m minus 1, and this should happen total m times. This should happen total m times, this should happen. Okay, this is the condition for km. This is the graph realization. This is the condition for km. Okay, is this clear? Like, okay, I can say this is the graph realization condition for km. This is the graph realization condition for complete graph. Graph realization means, if you have this, like, okay, if you have m minus 1, m minus 1, m minus 1, if your degree sequence is like this, m times, if this is your degree sequence, then you can realize a complete graph. So this is the graph realization condition. This is the graph realization condition for complete graph. Okay, is this clear? So you have this degree sequence. With this degree sequence, can you realize means, can you create a complete graph? The answer is no. Okay, and this is the graph realization condition for complete graph. Is this clear? Very simple point. Okay, so means, if this condition will satisfy, then you will get complete graph, then you can create complete graph. And if this condition does not satisfy, then you cannot get complete graph. So this is the graph realization condition for complete graph. Now let's see the same degree sequence we have, and then I ask you, okay, so let's assume this is the degree sequence 4, 3, 2, 2. From this degree sequence, can you create a tree? This is your degree sequence. Then can you create a tree with this degree sequence? Can you create a tree? Can you realize a tree with this degree sequence? Can we realize a tree? Tell me. Can we create a tree? So the again answer is no. Again, you cannot realize a tree, because I told you that in a tree you must have two. In a tree you must have two vertices of degree 1. Okay, so you already know this point. Okay, so basically, and also you can notice one thing. What should be the total degree of tree? In a tree, what should be the total degree? Tell me. In a tree, what should be the total degree? If you have a tree, then total degree should be what? Total degree should be equal to twice the number of edges. Number of edges equal to 2n minus 1. Number of edges is n minus 1. This is number of edges. So total degree should be equal to twice the number of edges. And you can notice what is total degree here. Total degree here is 11. Actually one thing, because you have total degree 11, so you cannot create any graph. So let me take, you cannot create any graph. Okay, so let me take 12. Now you can notice that 2 into 5 minus 1. So this equation does not satisfy. So I can say there is no tree. You cannot realize a tree. With this degree sequence, can you realize a simple graph? Any simple graph? Just think about it. Okay, let's think about it. Can you create any simple graph? Can we create any simple graph with this degree sequence? Can you try? Maybe can we create? Like for example, we need a degree 4 vertex. Okay, so this should be the degree 4 vertex. This is your degree 4 vertex. Then what we want? Now, you must have a degree 3 vertex. Okay, so this vertex must have degree 3. Now we have a degree 3 vertex, we have two vertices, we have 1 degree. Okay, so yes, we can realize a simple graph. So simple graph we can realize, but we cannot realize a tree. Okay, so did you understand the graph realization problem? Graph realization problem means some condition is given to you and you have to find out whether, okay, whether a class of graph can be created or not. So this is your graph realization problem. So what is this graph realization problem? Very simple. So what is this graph realization problem? Some condition will be given to you. That can be degree sequence or anything. Okay, normally degree sequence is given to you. So graph realization problem means from some condition. Okay, like for some condition, and that condition is normally, usually that condition is your degree sequence, usually degree sequence. So for some condition, can you create? For some condition, can we create, okay, or can we realize at least one graph? Can we realize, okay, so can we realize a class of graph, a graph of some class? Okay, can we realize a graph of some class? Like, can we realize a tree? For example, can we realize a tree? Can we realize a simple graph? Can we realize a complete graph? Can we realize, okay, so like that. So this is your graph realization problem. Some condition is will be given to you, normally degree sequence. From this degree sequence, you have to find, can you create a simple graph? Can you create a tree? Okay, so this is your degree sequence problem. Now let's move on. So this is the degree sequence problem. Normally, usually, basically, I told you that normally we have this degree sequence will be given to you, but some other information also can be given. Okay, so but normally this degree sequence will be given to you. So basically, we look at the degrees and we try to find out. Okay, we try to find out, like we try to find out whether we can create a graph or not. Okay, so you know already what is degree sequence. First let's understand what is the degree sequence. So this degree sequence, I told you, this is the sequence of degrees. Okay, this is the degree sequence. Like, okay, you have degree sequence, degree of vertex 1, degree of vertex 2, and so on and so on, degree of vertex n. And usually we write it, I told you, this degree sequence usually written in non-increasing order. This is usually written, we usually write it in non-increasing order. So normally we write it in the decreasing order, basically. Okay, in the decreasing order, we write this degree sequence. This is the definition of degree sequence. Now let's see our first problem. Our first problem is graph realization problem for pseudographs. You know what is a pseudograph? Pseudograph is what? That is any graph. Like, okay, what is pseudograph? What is this? Okay, in short, let's call it PG. In short, let's call it PG. Okay, so let's call this in short PG. So pseudograph. So tell me, pseudograph is what? In pseudograph, self loops are allowed. In pseudograph, self loops are allowed. In pseudograph, multi-edges are also allowed. Multi-edges are also allowed. Okay, so this is the basically pseudograph is any undirected graph. Any undirected graph that you can create. Any undirected graph that you can create, that will be your pseudograph. So this is the definition of pseudograph. We can create self loops. We can create multi-edges if we want. Very simple. This is the simple. This is the pseudograph. Now, what is the condition for pseudograph? Like, what is the condition? If I give you some degree sequence, what is the condition? The first condition will always happen for all the graphs. What is that? The one condition will always happen for all the graph. If you have a degree sequence, okay, then remember, for all graphs, what will happen for all graphs? It does not matter which graph. For all undirected graphs, whatever undirected graph you have, for all undirected graphs, few things you already know. For all undirected graphs, okay, whatever undirected graph you take, remember, for all undirected graph, few things will always happen. First thing, the total degree will be always equal to even. Okay, so the total degree will always equal to twice the number of edges. So that means it will always be even. The total degree will always be even. For all graphs, whatever graph you take, number of odd degree vertices will always be even. Okay, number of odd degree vertices. Number of odd degree vertices should always be even. Should always be even. Okay, so this is the idea. These things will happen. Always these things will happen. For all the graphs, these things will happen. Total degree for all undirected graph, total degree is equal to twice the number of edges. And this number of odd degree vertices, this will be one. This will happen for all the graphs, remember. Okay, so this will happen for all the graphs. Now let's see this. For pseudograph, what is the condition for pseudograph? The condition for pseudograph is very simple. This is the condition. Okay, what is the condition? The condition is saying that you have a non-negative integers. Okay, non-negative integers, because the degree of any vertex, that is always degree of any vertex, that will be what can I say? Degree of any vertex that will be always greater than equal to 0. Degree of any vertex is always non-negative integer. This you already know. This is always non-negative integer, degree of a vertex. Okay, so these three things will always happen. Now let's see the condition for this pseudograph. The pseudograph is saying that non-negative integer sequence you have. Okay, this is a degree sequence of some graph, of some pseudograph. Okay, here I'm talking about of some pseudograph, if and only if their sum is even. That's it. That's it. This is the only condition. No other condition is there. Okay, so this is the only condition. Means if the sum is even, you just calculate the sum of degree. You just calculate the total degree, and then if the total degree is even, then you can say that yes, pseudograph exists. Okay, so this is the condition for pseudograph. So I can say that, okay, given degree sequence, very simple. This is the idea that you have a given degree sequence. Some degree sequence is given to you, and for that degree sequence, some pseudograph exists. Okay, remember, some pseudograph exists. Some pseudograph exists. Some pseudograph exists if and only if, this is a if and only if theorem, if and only if total degree is equal to total degree. You just have to calculate total degree, and total degree should be equal to twice the number of edges. Basically, you have to count number of odd degree vertices. That's the simple point. Total degree will be twice the number of edges if and only if number of odd degree vertices is even. Okay, so this is the if and only if theorem. I can also say that if and only if number of odd degree vertices is even. Number of odd degree vertices is even. Okay, this is only thing you have to check. Now you can notice, like for example, let me give you some degree sequence I am giving you, and can you give me a graph? On one side I am giving you degree sequence, and on another side, can you give me a pseudograph? Like for example, if I give you this degree sequence 3,3, then can you give me a degree? Can you give me a pseudograph here? Can you create a pseudograph 3,3? Yes, very easily you can create pseudograph. Okay, so very easily you can create pseudograph. Yes or no? Very simple. So this pseudograph you can create. Okay, let's see this degree sequence 4,0,0. Can you create a pseudograph? 4,0,0. Yes, again you can create a pseudograph. Like this you can create a pseudograph. Okay, so this will be B, this will be C. So is this clear? So basically, because of this self loop, remember, because of this self loop and multi edges, you can create any pseudograph. As long as your degree, as long as your total degree is even, you can create a pseudograph. I give you a degree sequence, like for example, let's assume another degree sequence I am giving you. Let's take this degree sequence, like 2, 2, 4, 8, 0, 0. Let's assume this is your degree sequence, and maybe 1, 1, 1, 3. Okay, now let's see. Can you create a pseudograph? Can you create a pseudograph? Now let me tell you one thing. Actually, pseudograph you can very easily create. You don't have to apply your mind. Like, okay, you don't have to apply your thoughts. Pseudograph you can easily create. For this degree, you can create this pseudograph. This pseudograph you can create. Okay, for this you can create this. Like, okay, this vertex you can create. For this you can create this vertex. See, you don't even have to apply anything. For this, what you can do, you can create this vertex. You can create this vertex. Okay, like this. And then you have 0, 0. So for that E comma F isolated vertices, and for this what you can do, you can create G, you can create H, you can create one edge between them. Okay, one edge between them and two edges here. That's it. Okay, so are you getting this point? Pseudograph creation is very simple. Very easily you can create a pseudograph. You don't even have to apply any thoughts. Sorry for that. Okay, did you get it? Tell me. So for this degree sequence, can you create a pseudograph? Yes, very easily you can create a pseudograph. What you can do now, you can notice vertex A has degree 2, vertex B has degree 2, vertex C has degree 4, vertex D has degree 8. Yes, multiple can be there. I don't care. Can you realize? Can you create some pseudograph? See this. Some graph exists. Okay. Can you create some graph? Can you create at least one graph? Some graph exists. Some pseudograph. Some pseudograph can you create? Can you create at least one pseudograph? For example, if I give you this degree sequence 3, 2, 1, 1, can you create a pseudograph? For this, can you create a pseudograph for this degree sequence? The answer is no. There is no degree sequence because the number of odd degree vertices is odd. So there is no pseudograph. So this is clear. This is the condition for pseudograph. This is the graph realization condition for pseudograph. Given a degree sequence, some pseudograph, at least one pseudograph exists for that degree sequence if and only if total degree is equal to twice the number of edges. I can also say some pseudograph exists if and only if number of odd degree vertices is even. So this is the simplest, very simple. Did you understand? Graph realization problem for pseudograph. Now let me tell you, this is not important. This pseudograph is not important. So you can notice here. You can notice this is not important. This pseudograph, graph realization problem for pseudograph is not important. But this is very simple. That is the reason I am telling you. Okay, this is the very simple point that only if you allow self loops, you can notice self loops are dangerous thing. Yes or no? Can you notice self loops are dangerous thing? Like self loop means person is independent. Okay, like self loop means you are not dependent on anyone. Like for example, this vertex is independent. Okay, using self loop, it does not care about others. It does not care about others. Yes or no? So self loops are dangerous thing. Self loops and multi edges. Okay, so their combination is dangerous. Tell me one thing, these are multi edges or these are self loops? Like what should I say? These two edges, these are multi edges, right? Yes or no? These two are self loop, but they are multi edges. They are multi edges. Like these three are multi edges. Okay, you know what is a multi edge? Multi edge means the same edge. Okay, so you already know the definition of multi edge. Multi edge means two or more edges which are same. Two or more edges which are exactly same. Edges which are exactly same. Okay, so this is the idea. For example, if you have this A, B, then you can notice this E1, E2. This E1, E2 are multi edges. And if you have A, then this E1, E2, these are also multi edges. So you can notice in both the graphs, E1, E2 are multi edges. These are multi edges. Multi edges means two or more edges which are exactly same. So this is the graph realization problem for pseudograph. If you have some degree sequence, from that degree sequence, can you create a pseudograph? Can you create that? So this is not important for GATE exam, so you don't have to worry about it. But this is a very simple thing, extremely simple thing. Whatever degree sequence I give you, okay, for pseudograph, you just have to check how many odd degree vertices you have. Number of odd degree vertices should be even. Now the next, this is also not important. This is also not important. This is for multigraphs. Like, can you create a multigraph? Can you create a multigraph? Let's see. Multigraph means in the multigraph, self loop must not be allowed. Okay, you know this multigraph. In a multigraph, what should happen? In a multigraph, self loop is not allowed. This you already know. Self loop not allowed. So you cannot allow self loop. Okay, but multi edges can be there. You can create multi-edges. There is no problem with multi-edges. Multi-edges are fine. Now let me give you some degree sequence. On one side, I am giving you degree sequence, and on another side, can you tell me multigraph exists or not? Multigraph, does it exist or not? MG. So tell me, like, okay, if I give you this degree sequence, multigraph exists for this degree sequence? For this degree sequence, can I create a multigraph? Can I create a multigraph? And the answer is no. Very simple. Because you have two vertices. It means you have two vertices. It means you have two vertices A, comma B. One vertex is isolated. One vertex is isolated. Only one vertex is there. Self loop is not allowed. Self loop is not allowed. So definitely you cannot create any multigraph for this degree sequence. Okay, let's see this degree sequence. Like if I have 4, 2, 2. Now for this degree sequence, can you create a multigraph? For this, can you create a multigraph? Yes, I can create. See, I can create this A, B, C. I can create multigraph. This multigraph I can create. Okay, very simple. So this is the idea. Now, what is the condition for this? I can say, what is the condition for multigraph realization? Like if you have a degree sequence, can you create a multigraph or not? What is the condition for that? And the condition is just one more restriction. You have a degree sequence. For that degree sequence, loopless multigraph without self loop. Okay, so can be realized by loopless multigraph if and only if total degree must be even and the maximum degree should be less than or equal to the total degree of remaining vertices. The maximum degree should be less than equal to the total degree of the remaining vertices. So this is the condition for I can say loopless multigraph without self loop. Self loop should not be there. So I can say that, okay, loopless multigraph. This exists. Loopless multigraph exists if and only if two things you have to check. Loopless multigraph exists. Okay, there can be multiple. Some loopless multigraph exists if and only if two things you have to check. Total degree even. You have to check that total degree should be even, means number of odd degree vertices should be even. Okay, if and only if first number of odd degree vertices should be even. Number of odd degree vertices even. That should be even. And the second thing you have to check is the maximum degree should be less than equal to the total degree of remaining vertices. This is what you have to check. Like here you can notice the maximum degree is less than equal to total degree of remaining vertices. So now let's take the questions. Let's take some questions. So this is clear. Just only this condition you have, that maximum degree should be less than equal to the total degree of the remaining vertices. Okay. Now let's see the condition. Let's see the degree sequence. Some degree sequence, and here can you create a multigraph? Like if I give you this degree sequence 1 1 1 1 2 4. Now tell me, can you create a multigraph? Number of odd degree vertices is even. And you can notice that the maximum degree is less than equal to the total degree of the remaining vertices. So yes, you can just see this. The maximum degree should be less than equal to the total degree of the remaining vertices. And maximum is 4. Is this clear? The maximum degree should be less than equal to the total degree of the remaining vertices. Means the maximum degree should be less than equal to the summation of the remaining. Is this clear? Let me know. Is this clear to everyone? So the maximum degree, this is the maximum degree, and you can notice this maximum degree is less than equal to summation of the remaining degrees. So yes, you can create a multigraph. Let's create a multigraph. Let's try to create a multigraph. So you have a vertex which has 4 degree. This vertex should have 4 degree. This vertex has degree 2. Okay, so what you can do, you can create like this. Now what you can do, you can create vertex C, vertex D. So now you can notice this at degree 4, this at degree 2, this at degree 1, degree 1. Now still two vertices of degree 1 are remaining. So you can create like this, E, F. But that we don't care. We don't care which, okay, how many graph you can create, that we don't care, but we can create. Yes, multigraph we can create. Okay, let's see this degree sequence. 5, 6, 1, 3, 4, 7. Now tell me, for this degree sequence, can I say multigraph will exist for this degree sequence? Number of odd degree vertices is even. Number of odd degree vertices, that is even. And the maximum degree is less than equal to the summation of remaining degree. Let's see this one. 3, 3, 5, 6. Here, no, because the number of odd degree vertices is odd. So there is no multigraph. So this is the simple idea. And for this degree sequence, if I give you this degree sequence like 4, 2, 4, 2, 0, 0. What about this? What about this multigraph? Again, multigraph does not exist because maximum degree should be less than equal to this maximum degree should be less than equal to the summation of the remaining degrees. So here also multigraph does not exist. And if I give you 4, then also multigraph does not exist. Okay, so this is the idea. If I give you 10, 2, 2, 2, 1, 1, if I give you this, then also multigraph does not exist. Okay, because the maximum degree should be less than equal to the summation of the remaining degrees. This is the problem for, this was the problem for multigraph. For multigraph and pseudograph, these are not important. Again, I am telling you, okay? So these things are not important, but yeah, but the conditions are very simple. So you can just like, okay, the conditions are actually very simple. For multigraph, the condition is very simple. For pseudograph, condition is very simple. So these are the condition for graph realization of multigraph. But remember, these are not important. These things are not important. Now, this is important. Finally, this is important. This is for simple graph. Okay, because mostly they will ask you for simple graph. Because simple graphs are interesting. So what is the graph realization problem for simple graph? Like what is the condition for simple graph? Let's see. For example, tell me, if I give you this degree sequence, can you create a simple graph? Like 4, 2, 2. For this, can you create a simple graph? Can you create a simple graph? Simple graph exists or not for this degree sequence? And the answer is no. The answer is no. Clearly, okay, for this degree sequence, 3 vertices you need. You need 3 vertices. Total 3 vertices you need. Okay, and you can notice one vertex has degree 2. Okay, okay. One vertex has degree 2. Okay, okay, okay. But you can notice this degree 4 we cannot create. Okay, so this degree 4 we cannot create. So simply simple graph does not exist. For this degree sequence, we cannot create a simple graph. Like if I give you some other degree sequence, for example, 4, 3, 2, 2, 1, 0, 0. Can I create a degree? Can I create a simple graph from this? This is the degree sequence. Can I create a simple graph? For this degree sequence, can I create a simple graph? Let's check. Let's check. So vertex. Okay, this vertex should have degree 4. This should have degree 4. Okay, one vertex should have degree 4. B, C, D, E. One vertex should have degree 4. One vertex should have degree 4. Okay, definitely it should have degree 4. Next, you can notice that one vertex should have degree 3. Now two vertices have degree 2, 2. So this has degree 2, 2, 2. Okay, 4. And this has degree, this has, okay, and then F is isolated, G is isolated. So yes, for this degree sequence, I can say simple graph exists. For this, I can say that simple graph exists. I can say simple graph exists. Okay, is this clear? So the problem, did you understand? Like, okay, graph realization problem for simple graph. For simple graph, okay, just understand that degree sequence is given to you. For that degree sequence, can you create a simple graph? Can you realize a simple graph? So that is the idea. Now let me tell you, this simple graph is important. This simple graph is important. So for this simple graph, there is a concept of graphic sequence. There is a concept of graphic. A sequence is graphic, or I can say graphic sequence. Graphic sequence, or simply you can call it graphic. What is this graphic? Or I can say graphic. You can call it graphic, or you can call it graphic sequence. And what is the definition of this? Graphic sequence means a degree sequence for which simple graph exists. Okay, a degree sequence for which simple graph exists. I can say this is a degree sequence of simple graph. Okay, degree sequence of a simple graph. Degree sequence of some simple graph. Of some simple graph. Degree sequence of some simple graph. I can say this is the definition of graphic sequence, or I can say graphic. Degree sequence of some simple graph. Like this is degree sequence of some simple graph. This is a simple graph. For that simple graph, this is the degree sequence. This is the degree sequence. So this degree sequence is graphic. Okay, this degree sequence is graphic. This degree sequence is not graphic. So what is this graphic? Graphic means this is a sequence, or I can say degree sequence of some simple graph. Very simple. Okay, so we have to check whether some degree sequence is graphic or not. Whether some degree sequence can create simple graph or not. You have some degree sequence. For that degree sequence, can you create a simple graph or not? Okay, so this is the idea. Now, what is the condition for that? So we have a Havel Hakimi theorem. This theorem we have, and what this theorem says. First, we will understand this theorem. Then I will tell you the idea. Okay, like the idea of the proof I will tell you. But first, we will understand the theorem. Then we will solve questions. And at the end, I will tell you what is the idea at the end. Okay, so let's see first what this Havel Hakimi theorem is saying. This Havel Hakimi theorem says that this is a recursive. This Havel Hakimi theorem, this is recursive. Okay, what this Havel Hakimi theorem says? Havel Hakimi theorem. Havel Hakimi theorem. What this theorem says? This is recursive. Recursive means this is recursive. Means you have a degree sequence. Okay, some sequence you have. Let's assume some sequence you have. Okay, now I am writing this sequence in the non-increasing order. So let's assume you have some sequence like D1, D2, D3, and so on Dn. And I am writing this in the non-increasing order. Always remember, this is very important, that you should always write this in the non-increasing, means in the decreasing order. You should always write this in the decreasing order. Now, what this Havel Hakimi theorem says? This Havel Hakimi theorem says that this sequence is graphic. This sequence is graphic. Means this sequence is for simple graph. Graphic means this is for simple graph. So this sequence creates a simple graph if and only if this sequence creates a simple graph. If and only if this sequence is graphic. Which sequence? See, understand which sequence. You write in the decreasing order. You write in the decreasing order. Then I am saying that this sequence is graphic. Means for this sequence, simple graph will exist if and only if this new sequence that we create, from this we will create a new sequence that should be graphic. Okay, which new sequence I will create? See, delete this, and okay, after deleting this, from the next D1 vertices, you delete one. So you delete this, and from the next how many vertices? From the next how many vertices? D1 vertices. From the next D1 vertices, I can say, okay, like I can say some, I can say from the next D1 vertices. So these are D1. From the next D1 vertices, what you do? You remove 1. And the remaining are as it is. Okay, as it is. Is this clear? First, tell me this idea. Is this clear? For example, let's take example. Let me give you some sequence. Consider this sequence like 3, 3, 2, 2, 1, 1, 0. Okay, 0. Let's consider this sequence. Now, this sequence is graphic. What this theorem says? This theorem says that this sequence is graphic if and only if and only if the new sequence that you create, that is graphic. The new sequence that you create, and new sequence, how will I create? I will remove this. Always very important, you write in the decreasing order. Yes, this is in the decreasing order. This is very important. You write in the decreasing order. After writing in the decreasing order, what you do? After writing in the decreasing order, what you do? You delete this. And from the next three vertices, you delete 1 1. From the next three vertices, you delete 1 1, and the remaining will be same. The remaining will be same. So if and only if this is graphic. Again, recursively you can do. Again, this is graphic if and only if. Again, recursively you can go. Recursively you can go. Okay, if and only if the new sequence that I create, that will be graphic. Is this in the decreasing order? Please tell me. Is this in the decreasing order? Yes. Yes, this is in the decreasing order, because this is very important. This should be in the decreasing order. So let's delete this. From the next two vertices, I will delete 1 1. From the next two vertices, I will delete 1 1. This is graphic. Now you can stop here. You can stop here and you tell me one thing. Is this graphic? Is this sequence graphic? Like, from this sequence, can you create a simple graph? Can you create a simple graph? Can you create a simple graph? Yes, of course you can create a simple graph. A, B, C, D, E, F. Very simple. You can create a simple graph. Okay, you can create a simple graph. Is this clear? Saurabh, see, Saurabh, we delete this, and from the next two vertices, we remove 1 1. From the next two vertices, see, we delete this, and from the next two vertices, we remove 1 1. We remove 1 1. So we will get 0 0, and this will be as it is. This will be as it is. And you can notice this sequence is graphic. This sequence is graphic, because this sequence we can get a simple graph. Or you can go, if you want, you can go further. If you want, you can go further. Okay, you can go till end. So this sequence is graphic if and only if. Either you can stop here. See, either you can stop here and you can say, yes, we can create a simple graph. Okay, what you can do, you can stop here. You can stop here and you can say, yes, we can create a simple graph. Or you can go further. Or you can go further. Tell me, should I delete this? Please tell me, should I delete this? Should I delete this? No. No, 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 no. Very important. You should write in the in the decreasing order. Always write in the decreasing order. So first you write this in the decreasing order. First you write this in the decreasing order. Now you do. Now what you do? You delete this one. You delete this one. From the next one vertex. From the next one vertex, delete 1. So finally you will get 0 0 0 0. And once you get all zeros, you can stop. Once you get all zeros, you can stop. Here you can stop. Okay, at this moment you can stop. Once you get all zeros, that means yes, this is graphic. Once you get all zeros means this is graphic. Why this is graphic? Because all zero means this is your E5. This is your simple graph E5, A1, A2, A3, A4, A5. This is your E5. Is this clear? Let me know. So here you can stop here. When you get all zeros, you can stop. Or you can stop here. Or you can stop here. Okay? Or you can stop here. So first, let me know. Did you understand this? Now, what is the idea? What is happening here? The idea. Let's see what is happening here. See, idea. Let's see. This idea will make everything clear. This idea. What is the idea? Idea is this. See, what you are doing in the Havel Hakimi. In the Havel Hakimi, what you are doing? In the Havel Hakimi, this is your maximum degree. This is your maximum degree vertex. And then you have some other vertices. What you are doing? From this, what you are doing? You are deleting this vertex. This vertex you are deleting. This vertex you are deleting. And from the next delta vertices, you are deleting one, minus 1 minus 1. You are doing minus 1 minus 1. From the next delta vertices, what you are doing, you are doing minus 1 minus 1. Like, okay, these are your delta vertices. Let's, for example, A, B, and so on, C, and so on. So what you are doing, from the next delta vertices, what you are doing, you are doing minus 1 minus 1. Okay, and so on. And the remaining will be as it is. The remaining will be as it is. This is what you are doing. This is this Havel Hakimi theorem is doing. Why? What is the reason? The reason is very simple. If you delete a vertex of this maximum degree, for example, this is your vertex, and let us assume this vertex has maximum degree. This vertex has maximum degree delta. This vertex has maximum degree delta. If you delete this vertex, what will happen? If you delete this vertex, what will happen? If I delete this vertex, then what will happen? You can notice total delta vertices degree will decrease by 1, 1, 1. Yes or no? B1, B2, B3, B delta. Okay, and so on. B delta. So you can notice that for delta vertices, if I delete this A, if I delete this vertex, if I delete this vertex, if I delete this vertex, then you can notice that for these delta vertices, degree will decrease by 1, 1, 1, 1. For these delta vertices, degree will decrease by 1, 1, 1, 1, 1. For how many vertices? For how many vertices? For delta vertices. Because the degree is delta, means there are delta neighbors. These are the delta neighbors. These are the neighbors of A, delta neighbors of A. So if I delete this A, then the degree of these delta vertices, that will decrease by 1, 1, 1, 1. That's the idea. This is the idea of Havel Hakimi theorem. Is this clear? Let me know. This Havel Hakimi theorem, this is a recursive theorem. This is a recursive theorem. What this says? This says that you have a non-increasing, this is important. You have a non-increasing sequence of non-negative integers. This is your sequence. This can be realized by simple graph. Means this is graphic. Means this is graphic. This can be realized by simple graph if and only if what you do, you delete this vertex. What you do, you delete this vertex D1. You delete this vertex D1. Okay, and what okay, from the next D1 vertices, from the next D1 vertices, you remove 1, 1, 1, 1, and the remaining will be as it is. Okay, so this is graphic. If and only if this is graphic. If and only if this is graphic. Okay, is this graphic? Just check. Is this sequence graphic? Check it. What you will do? Very simple. If you want to check it, very simple. First of all, is this in the decreasing order? Yes, this is in the decreasing order. Okay, first of all, you check. Is this in the decreasing order? Yes, this is in the decreasing order. Then what you can do? You can delete this vertex. If you delete this vertex, then for how many vertices degree will decrease by 1, 1? Tell me. If I delete this vertex, for how many vertices degree will decrease by 1, 1? For 7 vertices. For the next 7 vertices, 3, 5, 7. For the next 7 vertices, I can delete, the degree will decrease by 1, 1. 3, 2, 2, 2, 2, 2, 1, 0. Okay, and 0. So this is what you will get. See, these zeros. Okay, one more thing. See, one more thing. Always you can remove these zeros. These zeros always you can remove. Why? These zeros you can remove. Why? Because anyway, these are isolated vertices. They will create isolated vertices. They will become isolated vertices. They are isolated. Yes or no? They are isolated. So you can always remove them. You don't have to worry about them. These are isolated. So these zeros you can remove because these are isolated. So these you don't have to worry about it. Just remove them. You don't have to consider them in the further process. In the further process, you don't have to consider them. You don't have to consider them in the further process because they will create isolated vertices. Okay, so this is what you got. Is this in the decreasing order? Is this in the decreasing order? Yes. Yes, this is in the decreasing order. So again, you delete this 3. You delete this 3. For the next 3 vertices, the degree will go by 1, 1, 1, 2, 1. Okay. This is not in the decreasing order. This is not in the decreasing order. So what you do? First, you convert this into decreasing order. First you convert into decreasing order. Okay, 2, 1, 1, 1. Actually, you can stop here also. Can you stop here? Tell me, can you stop here if you want? You can stop here also. Why? You can stop because this graph I can create A, B, C, E, F. This graph I can create. So if you want, you can stop here also because we can create a simple graph. Because we can create a simple graph, so you can stop here. Or if you want, you can go. If you want, you can go further. If you want, what you can do, you can go further. If you don't want to stop, you can go further. So you can delete this vertex, and then from the next two vertices, degree will go 0, okay, 1, 1, 1. Now here you can definitely stop. Okay, so here you can definitely stop, and here you can say this will be your graph A, B, C, D. So something like this. Okay, here you can stop. Or if you want, you can go further. If you want, from here, if you want, you can go further. Finally, you will get all 0. Akash is saying, sir, it is not necessary to go further. Are you can stop anytime. You can stop anytime. This is the recursive algorithm. Akash, this is recursive algorithm. This algorithm says that this sequence is graphic. This sequence is graphic if and only if this modified sequence is graphic. If and only if this modified sequence is graphic. If and only if this new modified sequence is graphic, and so on. This is a recursive algorithm. This algorithm is recursive at any time. At any time, this is a recursive algorithm. Okay, from this you get a new sequence. From this you get a new sequence. This sequence is graphic. This sequence represents a simple graph. You can create a simple graph for this if and only if you can create a simple graph for this. If and only if you can create a simple graph for this. If and only if you can create a simple graph for this. So at any time, okay, at any time you can create, okay, can you create a simple graph? Havel Hakimi does not say anything about connected. Yes, it does not say anything about connected. Okay, Havel Hakimi does not say anything about the connected. Very simple, just can you create a simple graph? That is the idea. Okay, so you can stop anytime. Anytime you can stop. If you know, if you already know this is a simple graph, if you already know that this is a simple graph, this can create a simple graph. If you already know, then you can stop. Is this clear? Or if you want, you can go till 0. If you want, you can go till 0, 0, 0. If you want, you can go till 0, 0, 0. That is your choice. So this is the Havel Hakimi algorithm. So the algorithm is very simple. But let me give you some tips and tricks. Before applying this algorithm, actually what you can do, before you apply this algorithm, what you can do, few things you can check. Okay, so like, okay, so for simple graph realization, if I ask you whether simple graph exists or not, so for simple graph realization, few things you can check before applying this algorithm. Okay, some degree sequence is given to you. Let's assume this is your degree sequence. Okay, in the decreasing order. So this D1, D2, and so on Dn. This is given to you. Then what you can check before applying algorithm? So the first thing, how to check? How to check whether this is graphic or not? This sequence is graphic or not? This sequence creates a simple graph or not? So the first thing what you will check? Okay, to check sequence is graphic or not. This sequence is graphic or not. To check this sequence is graphic or not. Remember, graphic means simple graph, basically. Okay, this simply means some simple graph exists or not. Graphic means some simple graph exists or not. Some simple graph exists or not. This is your definition of graphic. So this sequence is graphic. To check if this sequence is graphic, the first thing you will check is number of odd degree vertices. The first thing you will check is number of odd degree vertices, because in any graph, number of odd degree vertices should be even. Number of odd degree vertices, okay, number of odd degree vertices should be even. Number of odd degree vertices must be even. So this is what you have to check. Number of odd degree vertices, that must be even. that must be even. The next thing that you will check, what is that? The next thing you can check is what is the maximum degree. If you have n vertices, what can be the maximum degree in a simple graph? What maximum degree can be? The maximum degree can be less than equal to n minus 1. Okay, and the minimum degree will be greater than equal to 0. So the maximum degree will be always less than equal to n minus 1, and the minimum degree will be this. What is the third thing you will check? What is the third thing? At least two vertices must have same degree. At least two vertices must have same degree. At least two vertices. Okay, after this you will say, after this you will apply Havel Hakimi. Okay, after this you will apply Havel Hakimi. This is you will apply at the end. Now let's see some questions. Let's see this question. Okay, so try this, like 88666. So let's try this question. 88666 5322. 5322. Is this graphic? Is this sequence graphic? Means, can you create a simple graph from this? Can we create a simple graph from this? First, you count number of odd degree vertices. Number of odd degree vertices is 2. Okay, and repeated, like at least two vertices have same degree. At least two vertices have same degree. So let's move on. Okay, so here can you stop? Like, can you immediately stop? Can you immediately stop? No, you cannot. No, you cannot, because number of you cannot. Basically, you have to apply the Havel Hakimi, because number of vertices is what? See, number of vertices is n, 9, and the maximum degree, when number of vertices is 9, then the maximum degree should be less than equal to, then that should be less than equal to 8. That is fine. The maximum degree should be less than equal to 8. So you cannot. Okay, you have to apply the Havel Hakimi. So let's apply Havel Hakimi. So what you will do? Is this in the decreasing order? Is this in the decreasing order? Yes, this is in the decreasing order. So you delete this vertex. You delete this vertex from the next 8 vertices. From the next 8 vertices, delete 1, 1, 1. Okay, so 7, 5, 5, 5, 4, 2, 1, 1. Again, is this in the decreasing order? Yes, this is in the decreasing order. So from, okay, you delete this. From the next 7 vertices, delete 1, 1. From the next 7 vertices, delete 1, 1. So 3, 1, 0, 0. Is this in the decreasing order? Yes. So delete this. From the next 4 vertices, delete 1, 1. From the next 4 vertices, we will delete 1, 1. You can forget about zeros. These zeros, you can forget about them. Okay, these zeros you can, okay, you can just forget about them. These zeros. Only this 332 you have to care. Okay, this 332. This 332. So what you will do? Again, this is in the decreasing order. Yes. You will delete this. You will delete this. But there is no enough vertices. We don't have enough vertices. If you delete this from the next 3 vertices, if you delete this, then from the next 3 vertices, you should delete 1, 1. From the next 3 vertices, you should delete 1, 1. But we don't even have enough vertices. Okay, so that is the, I can say here, I can say not graphic. And this is a, remember, this is a recursive algorithm. This is a recursive algorithm. If this is not graphic, then this is not graphic, then this is not graphic, then this is not graphic. None of them is graphic. This is a recursive algorithm. Okay, is this clear? This is not graphic. Means for this simple graph does not exist. So for this also simple graph does not exist. For this simple graph does not exist. Also for this simple graph does not exist, because this is if and only if theorem. So this is the idea. So we cannot create. Let's see these questions. Can you try? 3, 3, 3, 3, 1. Can you stop here? Immediately can you stop? For this 3, 3, 3. This is the question. 3, 3, 3, 3, 1. How many odd degree vertices you have? 5 odd degree vertices. So you can stop. Okay, number of odd degree vertices is 5. Number of odd degree vertices is odd. Okay, that is 5. So you can stop here. So I can definitely say that this is not graphic. This is not graphic. Okay, what about this 2220? So what about this 2220? Actually, you don't even have to check it. This is your favorite cycle, A, B, C, D. Okay, this is graphic. This is graphic because you have a simple graph. Or you can apply the Havel Hakimi. If you want, you can apply the Havel Hakimi. So what you will do, you can apply Havel Hakimi if you want. But if you want, you don't need to apply. You can directly say that this is actually okay. If you want, you can apply Havel Hakimi. So it will happen that you will delete these two. You will delete these two. So from the next two vertices, you will delete 1, 1. Okay, and now here you can stop. Here you can stop. This will be A, B. Here you can stop. This will be A, B, C. Okay, let's see this one. Is this simple graph? 4, 4, 4. Is this simple graph? You can stop here. This 4, 4, 4. Can you create a simple graph for this? Definitely not. Because if you delete this, you don't even have enough vertices. You don't even have enough vertices. You don't have enough vertices. So this is not simple graph. Next, what about this one? 5, 5, 4, 2, 0. 5, 5, 4, 2, 0. What about that? 5, 5, 4, 2, 0. 5, 5, 4, 2, 0. Let's see this one. Again, there are 5 vertices. Just think about it. There are 5 vertices. There are 5 vertices and the maximum degree is 5. There are 5 vertices and maximum degree is 5. Or you can do this. You can delete this. There are not enough vertices. We don't even have enough vertices. Okay, so this is also not a graphic. So which of them is graphic? Which of them is graphic? The answer is only this. Only this one is graphic. So this is clear. Havel Hakimi. This is very simple theorem. Havel Hakimi. Very simple theorem. Just do recursively. Let's see this one. This is graph realization problem for tree. This is also important. This is also important. Graph realization for tree. Let's see this. So this is important. Graph realization problem for trees. Means can you create a tree or not? Can you create a tree or not? And the condition is very simple, and this is important also. Because why this is important? Because in the standard universities, these type of questions are many questions you will find. I have seen like almost every standard university has one question on tree. Like you have a degree sequence, for that degree sequence, can you create a tree? So this is also important. In the GATE exam, there is no question so far on the trees. There is no question on graph realization of tree. There is no question, but this is important, this tree. Let's see. And the condition is very simple. You know, okay, how many edges are there in a tree? Tell me, in a tree, how many edges? In a tree, if you have n vertices, let's assume you have n vertices, then what should happen? If you have n vertices, then what should happen? Number of edges. First of all, you tell me what should be the total degree? What should be the total degree? Then you know that number of edges will be equal to n minus 1 and total degree will be equal to twice the number of edges. Okay, so total degree, that will be 2 into n minus 1. And this is the condition. That's it. That's it. This is the condition. So you can notice for n greater than equal to 2, if you have at least 2 vertices, you have a degree sequence. You have a degree sequence non-increasing order. You have a degree sequence can be realized by a tree if and only if the total degree is equal to 2n minus 1. The total degree is equal to 2n minus 1. That's it. What you have to check? You have to check that total degree should be equal to 2n minus 1. This is what you have to check. And of course, this is connected also. Tree is connected also. What is the minimum degree is tree? Tree is connected also. So what should be the minimum degree in tree? What should be the minimum degree? That should be greater than or equal to 1. Minimum degree should be greater than equal to 1. Okay. So you can notice minimum degree should be greater than 0 in a tree. This is what you have to check. These things you have to check for a tree. Isn't it simple? You don't have to apply Havel Hakimi. You don't have to apply Havel Hakimi. Just do the summation. Just find the total degree. That total degree should be equal to 2 into n minus 1. And also delta, this minimum degree should be greater than equal to 1. This is the simple idea, very simple. So whatever sequence I give you, and then I ask you, okay, so whatever question, at least two vertices, this condition will apply for at least two vertices. This condition, it will apply for at least two vertices. Yes, you can check that also. Yes, very good. Apipsa, you can do that also. So for example, for tree, what you can do, additional thing, what you can do, for tree, you can check like this. One more thing you can check like this, that in a tree, if you have number of vertices is greater than equal to 2, then at least two vertices of even degree 1. At least two vertices must have degree 1. Must have degree 1. This also you can use. But remember, this is the if and only if theorem. This is not if and only if. This condition is not if and only if. This is not okay. Like I can say this is necessary but not sufficient. Yes or no? This is necessary but not sufficient. This is necessary. This is necessary for tree. This is necessary for tree but not sufficient. And you can notice this condition is necessary also sufficient. The total degree should be equal to twice the number of edges. Total degree should be equal to 2 into n minus 1. And you can notice the minimum degree should be greater than equal to 1. Okay, now you can take some examples. Like for example, you have a degree sequence and you tell me, can you create a tree for that degree sequence? Like for example, if you have this degree sequence, 1, 1, 3, 2, 4, 5, 6, 7. Oh, okay. So that's it. So tell me, can you create a tree for this degree sequence? Can we create a tree? Can we create a tree for this degree sequence? All you have to check, total 6 vertices you have. What you have to check for this? What you have to check for this? Only you have to check that. Just find the total degree. Just find the total degree. That will be, you can just see. So what is the total degree? That is 22. Okay. Next. So total degree is equal to twice into n minus 1. What is n? N is 7. 7 minus 1. Is it correct? Is this correct? So no. No, this is not correct. No, this is not correct. So no tree exists. So tree does not exist. Okay, very simple. Let's see this one. 6, 1, 1, 1, 1, 1, 1. What about this one? What about this one? Tree exists or not? Can you create a tree or not for this sequence? Yes, you can create a tree. Just check. Just check. Total degree is 12. Total degree is 12, and that is equal to 2 into 7 minus 1. Okay, and you can notice degree is greater than equal to 0. Every vertex has degree greater than equal to 0. Actually, what graph you will get? You will get a star graph. You will get a star graph. Okay, so like this, you will get a star graph. You will get. Let's see this one. Let's see this one. 6, 1, 1, 1, 1, 1, 1, 0. What about this? Tree exists or not? What about this? For this tree does not exist, because remember, in a tree is connected. Tree is always connected. Tree is always connected. So the minimum degree should be greater than 0. The minimum degree should be greater than equal to 1. What about this? What about this? Tree exists? Can I say for this tree exists? For this, can I say tree exists? For this, no, tree does not exist. For this, tree exists? Yes, tree exists. For this, tree will exist. Okay. So for this, remember, tree will exist. So tree is connected. Minimum degree is greater than equal to 1 when n is greater than equal to 2. When n is greater than equal to 2. So remember, this is a tree. This is a tree. Here the minimum degree is actually 0. So when you have one vertex, remember this point. So tree tree with n greater than equal to, okay, this, for this condition is important. Tree with n greater than equal to 2, these things will happen. These things like degree is greater than equal to, minimum degree is greater than equal to 1, and at least 2 vertices of degree 1. Okay, at least 2 vertices of degree 1. So these things will happen when you have n greater than equal to 2. Okay, let's see this GATE question. This is GATE 2010 question. What this is asking? This is saying that the degree sequence of a simple graph, the question is talking about degree sequence of simple graph, okay, is the sequence of degree of nodes in the decreasing order. Which of the following sequences cannot be the degree sequence, cannot be the degree sequence of any graph? Remember, this question is talking about simple graph. So the question is talking about simple graph. Okay, let's see. For simple graph, we have to apply Havel Hakimi theorem. Let's see the option number 1. How many odd degree vertices in the option number 1? 4. Okay, so option number 1 you will have to check. So let me check option number 1. You can do the remaining. I will do only option number 1. You can do the remaining. So 7, 6, 5, 4, 4, 7, 6, 5, 4, 4, 3, 2, 1. 3, 2, 1. Okay, so let me do this option number 1. See, I am doing option number 1. You can do option number 2. Abhipsa, you do option number 2. Akash, do option number 3. And Yuvraj, do option number 4. Okay, let's get the answer. So I am doing option number 1. Let me do option number 1. So what I will do? Again, the same thing. This is in the decreasing order. Yes, this is in the decreasing order. Yes. So I will delete this. If I delete this, from the next 7 vertices, I will delete 1, 1, 1, 1 from the next 7 vertices. So I will get 5, 4, 3, 3, 2, 1, 0. Forget about 0. You don't have to worry about 0. Is this in the decreasing order? Yes. Yes, this is in the decreasing order. So again, what I will do, I will delete this 5. And then from the next 5 vertices, I will delete 1, 1. So from the next 5 vertices, I will delete 1, 1. Okay. Next, is this in the decreasing order? Yes, this is in the decreasing order. So I will delete this. And from the next 3 vertices, I will delete 1, 1. From the next 3 vertices, I will delete 1, 1. And here I can stop. Here I can stop because I got a graph. I got this type of graph I got. Okay, so I can stop. So this option 1 is graphic. This option 1 is actually graphic. And the question is asking not graphic. The question is asking not graphic. So this option is not correct because the question is asking not graphic. Okay, so this question is not, this option 1 is not correct. So tell me about second. Second, is this graphic or not? The second one. Okay, number of odd degree vertices is even, so you cannot eliminate. So the second one, is this graphic or not? Abhipsa? Okay, no. Okay, what about the last one? What about the last one? Last one is also no. And what about this third one? This third is yes. Okay, so the question is asking which is not graphic, so the answer will be second and fourth. So the answer will be second and fourth. Okay, let's check this fourth one. Okay, let me do this fourth one also. 877 for practice. 877 64211 64211. Okay, so this is in the decreasing order. Yes, this is in the decreasing order. Delete this. From the next 8 vertices, there are no 8 vertices. There are no 8 vertices. From the next 8 vertices, we don't even have enough vertices. We don't have enough vertices. So I can say this is not graphic. This sequence is not a graphic. Okay, so this is quite simple. So the answer will be option D. This is another GATE exam question. What that will be? GATE 2014. A sequence is called graphic if there exists a simple graph. If there exists a simple graph with n vertices having this degree sequence. So this is the definition of graphic that is given to you. Okay, definition of graphic is given. Which of the following is not a graphic? Is not a graphic. Which of the following is not graphic? So let us see. Which of the following is not graphic? See, this will be graphic. This is actually very easily you can create graphic, because you can create A, B, C, D, E, F. So you can create this. So this is definitely graphic. Okay, this is very simple. This is graphic. And this is 1, 1, 1, 1. What about this one? This is also graphic. This is also graphic. A, B, C, D, E, F. Okay, so this is also graphic. So these are graphic. Next, this, let's check this one. 3, 3, 3. Let's check this one. What about this? Apply the Havel Hakimi. Apply the Havel Hakimi. So if you delete this 3, then here let's apply the Havel Hakimi. So this 3, 3, 3, this 3, 3, 3, 1. Okay, and this 0 you don't have to worry. You don't have to worry about 0. So here it will be, you delete this 3. If I delete this 2, then I will get 1, -1. Because of this 1, -1, so I can say no simple graph. So the question is asking not graphic. So the answer will be actually, the answer will not be A, B. The answer will be C. The correct answer will be C, because the question is asking not graphic. Okay, so very simple. And you can check this option number D. I think this will be graphic. Can you create a simple graph for this? Yes, this will be graphic. See, just apply the Havel Hakimi. Just apply the Havel Hakimi. 3, 3, 2, 1, 1, 1. 3, 2, 1, 1, 1, 0. This is the graph. So just delete this. Then from the next 3 vertices, you can delete 1, 1. Okay, so this will be 1, 0. Okay, and so on. Now you sort this. So once you sort it, then actually you can just stop here. You can stop here. You got your graph. Okay, you can stop. So you can stop because you got your graph. Or if you want, you can go further. Then you can delete this. Then from the next one vertex, you will delete 0, 0, 0. All 0 we got. So this is graphic. So this is graphic. Okay, so that's it. This is your chapter. This is enough for today. If anyone has any doubt, you can ask. So this is the Havel Hakimi theorem. Remember what we have seen? We have seen graph realization for tree, graph realization for tree, graph realization for simple graph. This is important. Graph realization for simple graph, Havel Hakimi. Graph realization for tree, just check the total degree should be equal to 2 into n minus 1. Okay, very simple. And tree must be connected. So the minimum degree should be greater than equal to 1. So this is what you have to check for tree. And for simple graph, apply the Havel Hakimi algorithm. And for pseudograph, just check number of odd degree vertices. Number of odd degree vertices should be even for pseudograph. And for multigraph, number of odd degree vertices must be even, and the maximum degree should be less than equal to the remaining total degree. The maximum degree should be less than equal to the remaining total degree. So this is the complete idea.